Okay, so this took quite a while to set up. I'm not really sure what's going on with this laptop here and how to get OBS to reliably stream OneNote. But anyway, uh, so you may remember last time I was talking about very high level picture, kind of ranting and raving about how I want to work on this project with an FPGA on this really interesting board. And my goal is to really try to turn that FPGA into sort of a GPU, a graphics processing unit, where we could have a CPU that's on the board running code, sending over graphics information to an FPGA, which would be fast enough to output over HDMI directly. So something that I realized I wanted to talk a little bit about. And by no means will this be a complete, exhaustive, or even necessarily informative view of how this works. But I wanted to talk a little bit about the NES hardware that I'm drawing inspiration from, as well as specifically the NES graphics system in a little bit more detail. And I may end up having to talk more about this in the future and talk about it in greater detail. Maybe look at some informative websites together and be able to kind of click around and explain some concepts that way. But let's start at a really high level view of the NES. So, like I said, it's a place where I draw some inspiration from. And so let's talk about first the basic box of the NES. Right, so you have your NES, and within that, there are certain pieces of information that come in, and there are certain pieces of information that will go out. And this is sort of like a kind of a block diagram, I guess, not really. All right, so in the world of the Nintendo Entertainment System, let's first talk about the inputs. And so this maybe is obvious, but you have your player 1 and player 2 inputs, right? Your controllers. And that is not, being facetious, but it's true. Part of how the NES works and the reason that it's interesting and interactive is you have input that's coming in from the players via these controllers. Okay, so those come in to your NES. The other really important input that you have is, I'm just going to call it your software. It's not really, in some ways, software, right? Because that's your cartridge. So you can, whatever game you want to play, all of the code for that game is sitting on a little tiny circuit board that's inside of this big plastic cartridge that you then insert into your NES. Right. So these are some basic inputs that you have. You have things like power and such, but that doesn't really apply when we're talking about how the system interacts and operates. So cartridge plus controllers, and what are your outputs? You have two main outputs with the NES, right? One is, video output, and that's going to go to your TV. The other is audio output, and that will go to your speakers or TV. And so depending on who you were, you either had the RCA jack little cables, the banana plug types, right? A yellow one and a white one, or you had together that coaxial cable that you'd plug straight into the TV that would give you both a video and audio signal. So what's going on in here, inside this box? Again, I don't mean for this to be, I don't want to try to make it an exhaustive painting of what the NES hardware is and all of its capabilities. So I'm going to keep this really generic and say, all right, so you have, in here you have some RAM, right, random access memory, and you have a CPU. That's going to run the code on the cartridge. Over here, you have your picture processing unit. And over here, you have your video RAM or VRAM. Okay. So basically what happens here, turn on your NES, the software that's in the cartridge is going to provide some code to the CPU, and the CPU is going to end up deciding, depending on what that code says, the CPU is then going to start to run that code, and it's going to perform the operations that are specified. That could include loading data from the cartridge into RAM. It could load data from the cartridge into video RAM. It could load code from the cartridge into RAM, theoretically, to run on the CPU. And the CPU can also load information into video RAM itself. Now, the picture processing unit will read values from video RAM, read information from here, and the CPU will mostly read and write data from RAM. And there are special ways for the CPU to, write information into video RAM also. What's interesting here is you're talking about one type of memory, and you have two different processors, your CPU and PPU, that are both interacting with it. And there's a whole set of details about how that data can be loaded. When are you allowed to change values over here? There are times when you're not allowed to change values from the CPU over here because the PPU is using and depending on this data to be reliable as it looks through it. And we'll talk about this again in the highest level of detail. The least level of detail. So our PPU is basically then taking information from video RAM, looking at it, understanding what it is, and outputting that as our video signal. And this is very reductionist, but really basically, does this work? So basically, okay. So basically, our CPU is basically our magical audio system. It's not exactly accurate. There's a few other things that happen to make audio work, but I'm not that interested in audio anyway. And basically, these are all the pieces involved in an NES. So board analog. So we just talked about NES hardware, right? And we said, okay, there's RAM, there's video RAM, there's a CPU, there's a PPU, and I can't remember the exact models here. I think it's using some form of 8502, the NES, and the PPU is very much a custom unit made by Nintendo. Back in those days, there weren't really any standards for how video systems should work, and every manufacturer of every system would often, roll their own solutions to get something working at the beginning of the 80s. Anyway, so in our Spartan Edge accelerator, what's going on? So the RAM, so the ESP32, that is our CPU, actually also has a built-in RAM. This is something the ESP32 can access pretty quickly. There's an awful lot of it on the system, plenty for our purposes. So the CPU, remember, the thing that's running the code is going to be the ESP32's cores itself. And these are pretty powerful, actually way more powerful than an NES is. So for the VRAM, and when we get deeper into the FPGA side of things, we'll get to explore this more. But my plan is that part of an FPGA's structure includes some memory. It's not a lot of memory, but I think it's enough. So FPGAs have something called block RAM, and you can write, when you design the FPGA implementation, you can say what RAMs do you want, how much do you want, and where do you want it to be connected within your FPGA system to do what you want it to do. So I mean, I think here, I'm going to get it wrong, but I think it was something like 450 kilobits, not bytes. Bytes would be great, but not kilobits, built into the FPGA. And then our picture processing unit, right, again, we want to take advantage of the FPGA that's on the board to do that. So that's basically how I think about the analogs between our NES side of things and what I want to do with the Spartan Edge accelerator. All right, so kind of the final thing I wanted to talk about was graphics. So I grabbed a couple of images, and we can kind of look at some of this a little bit. So how do I explain? So the Nintendo Entertainment System and a lot of other video game systems at the time used something called sprites. And the idea of a sprite, it was a relatively expensive piece of hardware, but it was very flexible because the more sprites you could support, a sprite could be a custom-defined image that could move anywhere on the screen, and so you could use it for main characters, you could use it for enemies, very flexible thing. The other thing that the NES hardware had in its graphics were tiles, tiles specifically for backgrounds. So the idea is, you may have Mario, and I probably could have found a good screenshot for this, but imagine that this screen, second, can I do this more easily? Imagine that you have this screen and you have divided it up into pixels, no, not pixels, into blocks. Whoa. So here's the thing about one of these blocks, right? Each of these blocks, oops, that's a very rectangular. Each of these blocks is, let's say, 8 pixels on this side, 8 pixels on this side. And if you take a look here, these are the actual, some of the tiles assembled in ways that maybe they look familiar from the original Super Mario Brothers game. And if we look at any one of these are actually many tiles, right? Because let's say it's 8 by 8. Well, this itself, the pipes, for example, are made up of some of the tiles that you may have a hard time seeing over here. So here you see this kind of dithered pattern. Look over here, you see that dithered pattern. So you assemble a bunch of these pieces on top of this grid of tiles. And you say, okay, so, over here I want this to be a pipe. So I'm going to put this tile here, and I'm going to put a longer tile here. This is our dithered pattern. And I'm going to have another one of the same image, but I'm going to flip it the other way around. I'm going to have our sitting here. But you see, the thing is, when you put this pipe down, it has to line up on these borders. Each of these tiles has to weird. Very weird. Okay, so each of these tiles has to line up with the borders that we've defined for how these tiles are supposed to work. And so you have to think about how you lay out all the graphics on the screen. If you want to use tiles, they have to lay out on the screen in a way that's going to match what you would expect. So this block, for example, let's just say it could be a question block. And it would have to always be, if it's not here, it would have to be one full block to the left, or one full block to the right, or above or below. It cannot be halfway in between. That is not allowed, because that's how tiles work. So this is a much less expensive part of the hardware, because basically what the graphic system does is it starts at the top here, and starts at the top of the screen, and it looks all the way across. And as it looks at each spot, it says which tile is supposed to be here. Okay, I'll load up that tile, and as I work my way across, I will take the image information and I will copy it from wherever in memory it sits, and I'll put it out on the screen over here. And as I go over here to the next line, I'm going to grab every pixel from whatever tile is supposed to be here, copy from memory, put it out to the screen. Do that all the way through as you go all the way across the screen once. And when you come back to here, you're going to go one line down. You're going to do this all the way across, all over again, and all over again. And all you have to do is find the one tile that's supposed to be at that spot. But that's how tiles work. Tiles are important, and they're going to be really important for my graphics plans as well, because again, they're relatively simple to use and implement, but they're not as much fun as sprites. So the right hand side here on this image, this is pulled again from Super Mario Brothers. You can see that the colors maybe are not what you expect for some of these pieces. That's because color information is not stored with the graphics themselves, but rather another part of the information that's in the cartridge will map specific colors to potentially some of these tiles. All right, but the left-hand side here, these are our sprites. So some of this should look familiar, right? You're seeing pieces of big Mario, pieces of small Mario. You see parts of Koopas down here. You see part of the mushroom here. Looks like a cheap part, I think. Parts of the piranha plants, some leaves. Where my Goomba at? Where's my Goomba? Some fireballs, Hammer Brothers. Goomba, there he is. That angry little Goomba, the top of his head, and then the rest of his body. All right, so sprites, like I said, they're more expensive to implement. They're also a lot more powerful. So we were just talking about this whole grid system. Well, a sprite can be anywhere on the screen. A sprite does not have to line up on these borders. So one of the things, again, is you're going to take multiple pieces of these graphics and you're going to lay them out side by side. So you'll use multiple sprites, and you can imagine if this is Mario, and this is going to be a really bad looking Mario, but he got his little feet and he's running, his hands, his hat, right? So Mario might be made up of 4 or 6 sprites, all kept together. So basically, when the CPU is running the software and it's deciding where is Mario, it's going to say, okay, Mario is here, but what that means is I need to tell the picture processing unit, put this sprite here, put this second sprite here, the third one here, the fourth one here, the fifth one here, and the sixth one here, right? So basically doing this, 1, 2, 3, 4, 5, 6. But again, this can be anywhere on the screen. So it doesn't mean that we have to have Mario in these, 6, right? Mario could be anywhere. So you could start drawing Mario, over here and say, okay, this Mario is not over here. And so, part of him could even overlap on this side a little bit, right? He's not bound by these lines. Can't hold Mario down. And all the other sprites on the screen enjoy the same luxury. Now again, though, because that hardware is somewhat limited, because you could have multiple sprites on top of each other. So change colors. Ooh, yeah, I can. Yes. Okay. So, Mario might be here, and you might have a mushroom that's going to be, here, right? And then on top of that, you could have a Koopa Troopa that you want to draw over here. I'm not very good at drawing any of these things. And then there could be a piranha plant that's going to be, somewhere around here, and it's doing its piranha plant thing. And so a lot of these sprites will overlap. And so remember before I was talking about how you might be in a situation where, with the tiles, you're just going straight across the lines. You're looking for the one tile that's going to be here. You're going to figure out what the color is supposed to be. You're going to copy all that information out and send it over to the TV. But at the same time, the other thing that's happening is you have to figure out if there's a sprite at any of these locations. And if you find a sprite, you got to say, oh, okay, there's a sprite here. Which sprite is it? What color is that sprite? And now make sure that that sprite information shows up instead of any tiles or other sprites that are behind it. So this is, I forget if the name is the right one, but basically the way I think about it is it's a pixel pipeline. There are many steps that happen. And again, all of this stuff is based on how televisions used to work, which again, you send that data out sequentially as you read all the way across. And actually, even modern LCDs work on basically the same principle, the same interface. So the idea is, you have a system where you're looking for the tile and a system where you're looking for the sprites that maybe are also the case. So you need to, load the sprite, right? You need to, check for a hit, like is that spot have a sprite on it or not? You need to then, get the color and copy the color. That is the color of the pixel. So you have a couple of things that all need to happen. And the thing is that even when graphics were simple, you can't do all of these things at the same time. Because remember, these systems, they work on a clock, let's say it was 8 megahertz. I would have to double check, but I don't think that in, 1 over 8 megahertz, which is, the fraction of a microsecond that you have, that you're actually going to be able to do all of these operations. So actually what you're going to be doing is, again, because it's a pipeline, you're going to do each of those things in one clock cycle, one tick of the clock. So it takes you 4 clock cycles to get an answer. And that means, while you are looking at, where on the screen you are, and you're outputting some information about this pixel, you at the same time, you are getting the color for this one, and you are checking for a hit on this one, and you're loading the sprite for this one. So basically, you have to do moves several pixels ahead so that by the time you need to broadcast this pixel information, it's gone through all 4 of these steps. So craziness, a lot of weirdness, but I really respect the idea of how these problems were solved. And the truth is that even in modern hardware design, as much as possible, you'll find that this pipeline concept applies. So even CPUs today will have a pipeline, because think about it, a CPU runs code, but in order to run the code, you still need to fetch the code from memory and then decode what that code is telling you to do, and then perform the operation. And so modern CPUs have pipelines with many stages in them, right? This sprite thing I'm talking about is only 4, but a modern CPU, they've had 11, 20, 30 stages, I don't know, in order to optimize the performance, because if any operation takes a smaller amount of time, then you can potentially have your whole system running a lot faster. As long as you can be sure that each of these calculations can be done within a certain fraction of time, then you basically, what you can do is you can say, let me take the longest one. So if this one takes, I'm just going to see, if this one takes 1 microsecond, if this one takes 0.5 microseconds, if this one takes 0.5 microseconds, and this is 0.05 microseconds, well, if I had to do them all in one clock cycle, right, then this whole thing would actually take me the sum of it, which is 2.05 microseconds. And my frequency is going to be 1 divided by that, which is, I don't know, I think it's give or take 500 kilohertz. But if I said, I want to break this up into a pipeline, and each one of these can happen on a separate clock cycle, one after the other, and so I can do operations for the later stages in advance and kind of almost run them in parallel, then I just have to pick the maximum time. So in the case of a pipeline, my frequency could be 1 divided by 1 microsecond instead, which is going to be, 1 megahertz. Okay, so, way faster, right? I can do that at double the speed. And all because I've designed hardware that's using a pipeline instead. So this was a big part of, circuit design back in the old days. That's still part of how you would design a digital system today. And it's part of how I think about the project that I want to, the thing that I'm trying to build as well. I don't think it's very interesting to get into board graphics yet, so hopefully this was again, I know it's a very cursory look into how the hardware of the NES worked, and especially the graphics system, but hopefully this helps to inform some of what I've been thinking about as to how all of this can work, why this is what I think is a very clever design, and why it could be a lot of fun to think about how to take this concept from the NES in terms of how it broke down its systems and build our own set of analogs with the modern piece of hardware.